I will be talking about liquid crystal defects. I'll explain the title, the first line of the title about halfway through, but this talk will be about liquid crystal defects as we go across the nematic to smectic phase transition and back. It'll overlap significantly with Danilo Liarchi's talk previously. What you're seeing here is a nematic sample just above the transition from nematic liquid crystal to smectic A liquid crystal. This image, these are both from experiment, is the same sample, same place in the same sample, but just inside the smectic phase. So just above the transition, just below the transition, very different morphologies, and I'll explain what these are in a bit, but they share important geometries inherited from the nematic into the smectic. So all the experimental results I'll show are from the lab of Dong Ki-yoon, done by the students Minjun Kim and Aram Se. They're at KAIST in Korea. I'm from Brown University. And the basic setup here, what's producing all these interesting textures in these liquid crystals, is that they're confined in thin films, a couple microns, with antagonistic boundary conditions, so-called hybrid anchoring. So at the air interface, there's homeotropic, perpendicular anchoring for our rod-like molecules, so the director field is vertical there. But at the substrate, it's the opposite. There's tangential or degenerate planar anchoring, and the substrate in this case is water. So the nematic liquid crystal has to rotate the director field through about 90 degrees, assuming strong anchoring. And this requires a combination of splay and bend distortions, which we've heard about in previous talks this morning. In the smectic liquid crystal, the rod-like molecules are assembled into layers, which really strongly prefer equal layer spacing. What this ends up meaning is that splay distortions of the director field, which becomes a layer normal, are okay. But bend is very costly. That requires changes in the layer spacing. As a result, the same boundary conditions are responded to by the smectic by spontaneously forming the structure called the focal conic domain, which Danilo introduced in the last talk. In this case, it's the toric or toroidal focal conic domain because the layers are the inside pieces of nested tori. Here, my line defect rests on the substrate, or sorry, the circle defect rests on the substrate, straight line defect coming out, and this is a special case of the focal conic domain with non-zero eccentricity, where the linear defects are an ellipse and a hyperbola in orthogonal planes, each passing through the focus of the other. And then so the layers in this case are those Cyclides of Dupin we heard about. In the case of the toric focal conic domains, these cylindrical domains can pack into a hexagonal lattice on the plane. And that's nice, for example, if you want to have an open regular lattice of colloidal particles or nanoparticles, they will go to the defects in the liquid crystal. So this is a nice way of self-assembling that. But back to these two images, these are very different ways of responding to the same boundary conditions. So the question I want to pose is, as you go across the phase transition, how does this structure, which only depends on Z, turn into this complicated 3D structure? And in the second part of the talk, I'll show more recent work about what happens when you take this smectic complicated 3D structure and melt back into the nematic phase. And before I get started on that, I have to mention that there are also defects in the nematic phase. These are the Boojums I mentioned in the title. They show up as fourfold crossings of dark brushes under polarized optical microscopy. And they are surface defects, which have a plus 2 pi or minus 2 pi winding in the plane of the substrate. As you step off the plane of the substrate, the director field escapes into the normal direction up, into the vertical direction up or down, so it's not singular off of the substrate. Okay, so here is a movie. I'm going to show you a movie of the phase transition taken by Minjun Kim. And we're starting in the nematic phase, where you can see occasional Boojums in the field of view. And this is polarized optical microscopy. A few frames in, Minjun is going to switch to quarter wave plate microscopy. So you'll see blue and orange indicating the opposite diagonals. So here we go with that. Boojums for a while. Cooling now. Here's quarter wave plate microscopy, but still Boojums. And now stripes. Stripes break up into rows of focal conic domains. And the focal conic domains relax and become more circular. So let me loop that through again. And this time, keep an eye on this Boojum. It does something special. It turns quickly into a big toric focal conic domain and slowly relaxes in size as its neighbors grow. Okay, so this is beautiful, but what's going on here? We knew the nematic phase has occasional Boojums. We knew the smectic phase, its ground state, is toric focal conic domains. We didn't know before if there was any morphology connecting the two. Now we have these two new morphologies, the stripes in the nematic phase just above the transition temperature, and the focal conic domains just below the transition temperature that provide a pathway from one structure to the other. And these focal conic domains are the elliptic hyperbolic kind, which means they have an orientation according to which way the major axis of the ellipse and the tilt of the hyperbola are oriented. And that orientation is always along the stripe direction. So this blue and orange oscillation means this, yes? Mainly the thickness of the sample is the limiting one, but it's an interaction of the anchoring strength and the elasticity of the smectic. How much the substrate wants it to be horizontal versus how much the layers resist bending through that 90-degree circle. Yes. Sure. So in each of these toric focal conic domains, there are two blue lobes and two orange lobes. So those indicate the regions in which the projection into the XY plane is along the diagonal going up and to the right, indicated by the lambda, the gray arrow. The opposite diagonal is the orange lobes. So this is just showing you that there's a circular, an azimuthally symmetric structure. It'll show up as blue, orange, as you go around by 2 pi. And then the extinction crosses, right, these black crosses, are the same as regular polarized microscopy. You'll get 4 under a circularly symmetric structure. In the case of these focal conic domains, you see there's just one blue and one orange in each one, which indicates this tilt, and we're seeing mainly this back region, the side closer to us and the side farther from us, show up as orange and blue. In the stripes, you're seeing oscillations about this original direction into the other diagonals. And I'll have pictures later about what that looks like, but it's oscillations of the in-plane angle about the original direction. No, this is what you get directly out of the quarter wave plate microscopy from the experiment. It's not false color. Right, so assuming you're at equilibrium, it's an energy minimization where if you had infinite thickness, it would just be set by, yes, they do. So it's limited by the thickness of the sample, but it's not directly proportional because you have this other length scale of the elasticity over the anchoring strength. Those interact to give you the energy landscape for one focal conic domain, and then you want to minimize over the size in a packing, so the energy per unit area. So the +1 Boojum gave us this radial arrangement of stripes. Oh, and you can even see in this dislocation of the stripes, the dislocation in the rows of focal conic domains. The -1 Boojum, which looked originally a lot like the +1, gives this diamond arrangement of stripes, and that breaks up into a diamond arrangement of focal conic domains, and that slowly relaxes also into toric focal conic domains. So, oh, and this big toric focal conic domain that showed up earlier comes from the +1 Boojum, a particular kind of +1 Boojum, the kind that escapes up, which we call the +1 converging Boojum, because of the similarity in director fields. Both are circularly symmetric, and both have this escape up off of the substrate. There's also a +1 Boojum which escapes down, which we call the diverging Boojum, which has exactly the wrong director field, and so this does not transform directly into a big toric focal conic domain. Okay, with that said, I want to understand why the stripes form just above the phase transition, and then how can we understand the stripes breaking up into these aligned focal conic domains? Yes. All I can say, and I'll have images in about halfway through the talk that'll show they become centers of, they're sort of like the -1 in that the stripes are organized around them, and so the rows of focal conic domains are organized around them, but there's no obvious placement of the focal conic domains in relation to where that Boojum was. Not by this method of microscopy. Maybe Yvonne Smolyuk's group, maybe Haley Sohn could do that with some fancy technique, but this kind of microscopy does not distinguish between converging and diverging. However, because only one type turns into the toric focal conic domain, afterwards we know which ones are converging. Okay, so to understand first why the stripes appear, we look to the Frank elasticity of the nematic phase, but as we approach the smectic phase. So in the ground state, the director field is spatially uniform. The Frank or Oseen-Frank free energy, which we've seen before in similar forms, penalizes splay, twist, and bend. And there's also this total divergence term for saddle splay, and those kinds of deformations are shown here. In the smectic phase, we want this director field to be normal to a family of layers. And the energy for a smectic, 3D smectic, can be written down as the integration over all the layers of the mean curvature of the layers squared, and the Gaussian curvature with some k bar, and the bulk modulus, which penalizes deviations of the layer spacing from the preferred layer spacing d0, dilation or compression. And this term is strong in the sense that the length scale you get from root k1 over b is of order the layer spacing, so it's microscopically small, which means the smectic really prefers to bend at mesoscopic scales over having changes in the layer spacing. The layers prefer to bend. What that means from the point of view of the director, the layer normal, is that splay is okay, as I said before, but bend in the director means that the layer spacing is changing. And so that becomes very costly. Twist is also going to be very costly because twist in the director field is just geometrically incompatible with having layers. Saddle splay turns out to be the layer Gaussian curvature. So as we approach the nematic to smectic transition, there's a divergence of the ratios, k3 over k1, bend to splay, and k2 over k1, twist to splay. Now, in this initial nematic geometry from the hybrid boundary conditions, we already had splay and bend. There was no twist there originally, but there was splay and bend, and the bend is going to be increasingly an energetic problem. So I can do a linear stability analysis and ask when are stripes energetically favored, at least in linear stability. So this theta naught, this angle, the polar angle of the director, can be analytically found. Here I'm giving a finite anchoring strength to the substrate, anchoring strength W, penalizing how far out of plane you are. On top of this, I'm going to add a sinusoidal undulation to the polar and the azimuthal components of the director. This phase offset beta turns out to just be pi over 2. And this sinusoidal undulation, so blue here is indicating how far off you are from the original orientation locally. The sinusoidal undulation changes the elastic and the anchoring energy by some total amount delta F, and I want to know when does the total energy decrease by adding these stripes as a function of the wavelength of the stripes. And what I find is that stripes are stable from this linear stability calculation in this region of this plot where on the vertical axis I have the stripe wavelength in units of the sample thickness. Correct, correct. I'm looking locally and asking, right, ignoring the Boojums for now, when would stripes appear in a uniform in X and Y nematic? Yes, thank you. And so for K3 over K1 less than 10 or so, which is for the nematic phase, there are no stripes ever. But as you get to large K3 over K1, as you go toward the smectic, there are stripes which quickly go to wavelengths comparable to the sample thickness, which is what we see. There's an upper critical K3 over K1, which corresponds to the thickness of the sample times the anchoring strength. If the bend elastic constant is stronger than that, then the system will just be uniformly homeotropic. The director field will be vertical. If you're familiar with the Friedrichs transition, it's similar except driven by the bend elastic constant instead of the external field, or driven by the anchoring instead of an external field. And so breaking the energy apart into its components, there's a cost to having this stripe in splay, twist, saddle splay, and anchoring. The only term that saves energy is bend. And so bend alone is driving the stripe instability. As the baked-in bend of the original structure increasingly gets more costly, it'll want to deform out of that structure, form stripes, and so the total energy here is very slightly negative as a result of adding this stripe configuration. So that was linear stability, but I can also numerically minimize the energy and find when, yes? Yes. Yes, so the anchoring strength at the air interface is, of course, actually finite. Also, I assume it to be infinite because in practice, the length associated with that anchoring strength in relation to the elasticity is larger than the sample thickness. So, yeah, I assume that to be constant. No, I take that back. It's much stronger. It's not larger, but the anchoring strength is much stronger than at the substrate. So it's a simplification to just have one anchoring strength. So I used the Landau-Dijen Q tensor model, which takes the director Nij as Qij with this prefactor that gives the degree of order. There's an integral over the bulk of the phase and gradient energy densities and an anchoring energy at the substrate. The phase energy just tells us that we favor having nematic. The elastic energy I write as these four different terms, which lets me independently vary K1, K2, K3, and K24. And the surface energy is degenerate planar at the substrate with this anchoring strength W using a formula from Fournier and Galatola. Putting all that into this setup and minimizing the energy, I find stripes come out that look very similar to what I assumed for the linear stability calculation, just with a slightly larger wavelength. And I assume the sinusoidal undulation of both the polar and azimuthal angles, which looks pretty good in the bulk. Here's in the midplane. But at the substrate, z equals 0, something different is happening. Here, from the numerics, we see, instead of a sinusoidal undulation, a fan-like undulation. Slow variation from minimum to maximum angle, and then a jump back down to minimum. That's what's happening here with this jump from one diagonal to another. And we believe that this is the precursor to walls between focal conic domain rows in the smectic. So here, from one row to another, you have the slow rotation from orange to blue, and then a jump back to orange in this wall between rows of aligned focal conic domains. Okay, and then why from the stripes do we get these rows of focal conic domains? The focal conic domain rows are the natural smectic successor configuration, kinetically speaking, to what the stripes were doing before. Because if we look at that fan-like undulation in the plane of the substrate, that's recapitulated by each row of focal conic domains. And in a side view, this rotation from top to bottom of the director is recapitulated by the director field, the layer normals of the focal conic domains. But that's only true of the back part of the focal conic domains. the front part gets it completely wrong. It's tilting in the other direction, so it would be tilting backward against the stripe direction. And the smectic knows this in some sense. When the focal conic domains first appear, you may have noticed that they weren't completely round. They each take a bite out of the one behind it in some sense. The region in front of the hyperbola is cut off because it has exactly the wrong director field. And you can see the hyperbola here in bright field microscopy as this dark dot. And the ellipses show up as these incomplete arcs here. So this is a qualitative understanding. The quantitative understanding is still missing. And we heard in Danilo's talk previously how difficult it is to simulate smectics in 3D. But we hope going forward that to have some more quantitative understanding, for example, of what kinds of defect structures are needed to join this focal conic domain, incomplete domain, onto this one. So zooming out, there's this lattice of Boojum, this Boojum network of plus and minus defects. I'm going to go a little bit quickly through this, but just to say that we have both +1 converging and +1 diverging. I'm using this nail head notation where the side closer to you has the nail head. So viewing from above, I can put these nail heads on the experimental image, fill in some sensible way, and I wind up with this alternating -1 +1 -1 +1, except from row to row I alternate between converging and diverging +1 Boojums. So this word Boojum was taken by David Merman from Lewis Carroll's story, The Hunting of the Snark. I want to know what information goes away when the Boojums disappear in the smectic phase. It turns out that there's complete reversibility, almost complete reversibility, cooling into the tilted focal conics and then heating back up. Cooling to the toric focal conics, however, reverses this, or erases this reversibility. So this nematic structure and this nematic structure are almost identical. This one is completely different. If we look at what happens when a focal conic domain, toric focal conic domain packing melts into a nematic structure, with this nail head notation, we have this inside of the toric focal conic domains, but everywhere outside is pointing straight out at us. As we melt back into the nematic, the director will tilt back into the horizontal plane with some component, and just filling in these nail heads in some sensible, continuous way, it's natural to expect a -1 in between every pair of focal conics and a +1 diverging in each of the voids. And this is cute because now we have some graph where the vertices are the focal conic domains, each edge has a -1, and each face has a diverging +1. So the total Boojum charge is just vertices minus edges plus faces +1 because there's an outside face to the whole thing too. And since chi, the Euler characteristic, is 2 for any planar graph, that means the total Boojum charge is +1. So any information about Boojums from the nematic phase as we cooled into the smectic completely disappears once we get to this stage because any subset of the toric focal conic domains looked at independently has a Boojum charge +1. That's not the whole story because there are also disclinations, and here I'm showing a simulation of the nematic but with the smectic as the starting configuration. And we can see that Boojums of +1 type appear where the focal conic domains were. In this case, there were disclination lines, and then there's this coarsening process. And there's these system-spanning disclination lines, but let me now take away the periodic boundary conditions and replace them with free boundaries. And I wind up with 3 +1 Boojums, 1 -1 Boojum, and a disclination line, which if I freeze time here, has -1/2 cross-section in the plane, but +1/2 cross-section in the opposite plane. And that replaces these 3 defects here. So far in the numerics, this +1 diverging that I expected hasn't shown up yet. And I'm still exploring why exactly that should be. So with that, let me leave my conclusions here. And if there are further questions, I'm happy to discuss.